Guten Tag und willkommen zu OpenNMS Geschäftsbericht. No, that's it. I said I know that phrase and I practiced ein großes Bier bitte. Schwarzbier, I like the black beer. Hi, my name is Tarus Balog. I'm one of the people who works on OpenNMS. The very first OSMC I came to was in 2009, which was the first year this conference was called the OSMC. And I love this conference, it's great. I appreciate you coming to hear me because I'm not a singer. But today I wanted to do a discussion of the OpenNMS annual report. So what have we done since the last OSMC back in 2017? Before I get started to talk about OpenNMS, I want to address something that's been bothering me. Monitoring sucks. So around 2012, this hashtag started appearing, monitoring sucks. And I've been working on OpenNMS for about a decade at that point in time, and I was like, why does monitoring suck? But everyone was saying, monitoring sucks, monitoring sucks. This slide here, I think, was from Chris Boitart at this conference. So I even put this up here. And so I've been doing a lot of thinking about it. And I do many presentations about OpenNMS. And so I was at a conference in Scotland, and this guy named Neil from BT, at the end of my talk, he said, the purpose of network management is to get rid of people. And I was kind of insulted about that. I mean, it's like he's saying, well, you can be replaced by a script. And I'm like, so I think part of monitoring sucks comes from people thinking that monitoring's unnecessary, that you don't need monitoring, and that monitoring's no fun. And I have seen organizations where if they bring on more servers, they have to bring on more people to manage them. And that shouldn't be the case. Your solution should scale. And I've been in situations as a consultant where people were doing very boring things every day because the same things would happen. And I was like, your network management platform should allow you to get rid of the boring things so you can focus on the new things. I mean, every single conference I go to, you learn about NFV and software-defined networks. The technology just keeps growing, and there's no way we could automate all of that. So we want to create a monitoring platform in such a way that we can produce monitoring love. So this is our mascot, Ulf. He is actually with me today. Let's see if I can find him. In my bag. Here we go. This is Ulf, so I will put him here. He was given, we had a conference for OpenNMS, and we had people from Germany, and we had a man from New Zealand. And since the Germans had come the farthest distance west, and he had come the farthest distance east, he gave them this Kiwi, and he's now Ulf. And he's our mascot, which is great. When I do this talk in New Zealand, they love it. So anyway, so monitoring love. Now, how many people have heard of OpenNMS? You got a few? How many people actually use it? Oh, good. We have a few hands. For those of you who don't know, the OpenNMS project got started in 1999, and I got involved in 2001. And in 2002, the people who started OpenNMS decided they weren't going to work on it anymore. They were investment funded. The investors did not like open source, and so they said, we're not going to work on this anymore. So I took it over. And I was told when you start a business and you get into an elevator and someone sees OpenNMS on your shirt, my luggage showed up an hour ago. So I actually have a Singa shirt on underneath here, but don't tell anybody. But someone sees OpenNMS on your shirt and they go, what's OpenNMS? Well, you have about 30 seconds to tell them. So I came up with this. OpenNMS is the world's first carrier-grade network monitoring platform built on the open source model. Ding! I'm a nerd. I'm a geek. I hate it when I get, we are the paradigm-shifting, synergy-building, market-leading solution for all your Kubernetes, Docker virtualization needs, cloud. I just hate that. So I wanted to break down everything I've highlighted here. When I say world's first, we've been around since 1999. The only other project around at that time was Nagios. Nagios put its code on SourceForge. If you remember SourceForge, think of it as GitHub for old people. So on SourceForge in January of 2000, he Ethan Gausted posted the first Nagios code, and we posted our code in March of 2000. So world's first. When I say carrier grade, we started out with this idea of monitoring hundreds of thousands, if not unlimited devices. Now, a lot of projects start out monitoring a few devices, and then they have to grow. We started out saying we want to monitor unlimited devices. Now, the application platform piece is very important. OpenNMS is an application. You can download it, you can install it, you can point it at your network, and you will get some information. But where OpenNMS starts to shine is when you customize it. And the way I like to describe this, and my wife hates me for this, but my wife is an accountant, and she manages a $2 billion budget. And I joke, she manages it with Excel. Now, the truth of the matter is they have a lot of proprietary, expensive software that creates the spreadsheets that she uses. Think of Excel as the accountant's Grafana. You know, it's like all this data feeds into Excel, and she uses that. If I bought a copy of Excel and went to Microsoft and said, hey, where's my budget? They'd laugh at me. They go, what do you mean? You have to make it. So what I try to tell people is go into OpenNMS with the idea that you're going to customize it. And then finally, open source. Every piece of code that is called OpenNMS is available under an open source license. Some of them are restrictive, like the AGPL for the product, but we have libraries and stuff that we license under Apache and other permissive licenses. But it's open source. There's not a piece that you have to, pay for to get the extra features. Enough of that. Okay, our goal, millions of devices, billions of metrics. And this is a slide from one of our customers. This is a 6-month period where they averaged 20,000 data points stored every second. So we were collecting 20,000 data points and sticking them into a Cassandra cluster. That's 1.75 billion metrics a day. So when you multiply that times 180, roughly 180 days, you're talking nearly 300 billion metrics. So that's what we're going for. We want to make this even bigger. Now, I'm here to talk about our horizon. So I love the fact that NETWAYS is advertising for us right here. So widen your horizon. It's even purple, just like our purple horizon color here. So that's what that means. Don't let Bernd or anyone tell you different. So Horizon is our rapid release. We do between 3 and 4 releases a year of OpenNMS Horizon. And we've done 3. I went and looked. We've done 3 since the conference last year. So I wanted to talk about the features of Horizon 21, which mainly concerns a visualization tool called OpenNMS Helm. It's an application that runs on Grafana. I want to talk about OpenNMS Drift, which manages flow data, so telemetry data, such as Netflow and Sflow. And then the real exciting stuff is Horizon 23, which is 2 projects that have, Horizon 23 was just released maybe, 2 weeks ago? It contains a project called Sentinel for distributing OpenNMS functionality, and Sextant, which is our machine learning piece. So Monitoring Sucks was basically started by this guy named John Vincent who wrote a blog post. Again, I'm old. Back in 2012, we had this thing called a blog where you would put stuff, and he had this long post about why he hated monitoring. And one of his things was having to choose between a poor, he used a much stronger word, but he says having to choose between a poor interface and great monitoring or poor monitoring and a good interface. We are definitely in the former. I think OpenNMS does great monitoring, and a lot of our big customers integrate with us via APIs, so they don't really use our interface. But we want to improve it. And when Grafana came out, everyone knows Grafana. Everyone use Grafana? You know what I'm talking about? So OpenNMS was actually the first third-party data source for Grafana. And for Horizon 21, we created an actual application called OpenNMS Helm. So you can go to your Grafana installation, say install OpenNMS Helm, it'll download and install OpenNMS Helm, and this will give you 2 data sources. There are 2 types of data sources. There's one for performance data. So this is your graphs. So you have your graph data, and there's one for alarms, which is the fault data source. Now this one is set up for one instance of OpenNMS, but I could have multiple. So if I had 3 or 4 OpenNMS instances, I could aggregate them all under one Grafana instance. And this is kind of what Helm looks like. I took the screenshot this morning. I do use OpenNMS to monitor my soda machine. I bought a soda machine a few years ago and put a computer in it so that I could monitor it. And so if you look right here, Diet Pepsi, we are actually almost out. I take the number of Diet Pepsis we put in the machine minus the number that we sold, and that value is 3, which happens to be the threshold that tells me I need to go and put more Diet Pepsi in the machine. No one likes Diet Pepsi, so we're going to put Dr. Pepper in there next. So I'm just waiting for that to run out. But you can have, one of the features that was that we've already talked about at OSMC is called the OpenNMS Minion. And it is a little software application you can distribute OpenNMS functionality. And so I have one at my house. I have a farm. I have an 8.5 hectare farm in the middle of nowhere. And it's called Sort of a Farm. Get it? Sort of a farm, sort of a farm. And so I have a Minion running at my farm, monitoring my devices, and then the default alarms are for the main instance of OpenNMS at our office. And so you can see there's a little histogram telling you what alarms are there. Then you can actually see the alarms. It's bidirectional, so you can right mouse click and either bring up details, you can acknowledge, and, well, in this case, unacknowledge, escalate, clear. You can create trouble tickets, all from Grafana. And then you can actually add your data as well. This is our circuit at the office. We average about, it looks like about 10 meg in and 10 meg out with some peaks. We integrate with R that allows you to do trending. So this is actually, you know, I took the screenshot last week. So you can see that this is the trend for, this actually took a screenshot this morning. So there we are on 611 is here. And so you can see that over the next 4 weeks, we expect our outbound bandwidth to increase a little bit and our inbound bandwidth to increase a little bit. So that's a way where we can get rid of the visualization sucks part of network monitoring. Now, the next thing I want to talk about is in Horizon 22, OpenNMS Drift. We were approached by a very large company to gather flow data, which is basically who is talking to whom. Now, I don't know about the requirements in Germany, but in New Zealand, if you're an ISP, you not only have to store the data, you have to store the payload. So if the police show up and say, hey, we want to know what this IP address was looking at 3 weeks ago, which I think is ridiculous. But a lot of companies are saying you have to store the metadata, at least which IP address was talking to what IP address. And this is one way to do it. So you could send from all your routers, you could actually send that information into OpenNMS, which we collect it and store it in Elasticsearch for scalability. So we dump all that into Elasticsearch. Now, when I say telemetry data, there's 2 types of telemetry data. There's performance data, so it's just like with SNMP. Everyone hates SNP. I like SNP. But this idea of CPU utilization, memory utilization, bandwidth, that can come from protocols such as Juniper's JTI or Cisco's NXOS. Then there's flow data. So we support IPFix, Netflow 5, Netflow 9, as well as Sflow. And at Sflow, you can actually do a little bit of both. You can get performance data as well as flow data. So how does this work? Well, the applications, this is what's running Netflow or Sflow, et cetera, talk to a listener. So they connect to a port on OpenNMS, and or they connect to a listener. It's not necessarily a port on OpenNMS. And that data is stored and passed to an adapter. Now, for each listener, you can have more than one adapter. Well, why would you need that? Well, take Sflow data. One adapter might be, I'm going to convert this into performance data, and one may be, I'm going to convert this into flows. Now, I'd mentioned the Minion. The Minion is this little piece of software. You can run it on a small box. You can run it on a big box. You can actually use that as your listener as well. Come on. There we go. I don't know about the battery in this thing. I always worry that it's going to run out right in the middle of a presentation. And in this case, what will happen is the Minion will collect the flow data and then forward it on using a messaging bus. The default messaging bus that comes shipped with OpenNMS is ActiveMQ. But most of our large installations use Kafka, and we support both. I don't know if these are familiar terms for you, but just think of it, this is the thing that just collects all the messages from the various pieces. And I'm going to talk about that in about 2 more slides. So the Minions can collect data, so I could have them in remote offices, I could have one at my house, and then I could forward this data onto a central OpenNMS, which would process it and store it. Now, When I talk about processing it, some of you who've dealt with flow data may go, well, I can just use Logstash. I can just send flow data to Logstash. Logstash will stick it in Elasticsearch just like you're doing. I don't need you, you suck. Monitoring sucks. And I'm like, well, one of the things that OpenNMS does that the default systems don't is we enrich the data. So when a particular piece of data comes in, we can look up SNMP stuff in our database and add information about the interfaces. We can add a category information, node information, a bunch of other stuff. And I believe we're one of the few that actually adds a when the Netflow started and when it stopped, so you can actually see how long the flow was. Some of these other places will just tell you when it stopped. So the process is this. We have this process called Telemetry D. Now, our app is written in Java. Okay, no one audibly groaned. I saw a few people roll their eyes. But it's written in Java, and it's made up of these processes we call daemons. So our polar daemon is called polar D. Our collector daemon is collect D. This is telemetry D, because it's our telemetry daemon. So the telemetry daemon adapters take all these different data, all these different flows, and convert them into a canonical form. So they basically create a message that makes the Netflow flow and the IPFix flow look just like the Sflow, and vice versa. Then we tag them with an application name, so it might be an HTTP flow, it might be an SSH flow, etc. And then we enrich it. We add this metadata, and then that all gets dumped into Elasticsearch. And now we have a REST API that you can use to query all this data. And of course, since Helm is our visualization tool, all this data can be sent to Helm. Now, why do we care about flow data? We have SNMP, that's all we need, right? Well, here's an example from a live system. The distance between this graph, even though it's about 2 meters here, is 4 seconds. So this is 4 seconds of data. And as you can see, there was a little tiny flow here. It's probably about a millisecond long. Slightly longer one here. Here's one that lasted almost, it looks about a quarter of a second. So you can get a level of detail that you can't normally get. I don't know about, I saw you look, I don't know how useful this particular example is, but I am telling you that you can get down to that kind of level of detail, which is a lot of the reasons why people want this data. Now, we are collecting, in production, around 100,000 flows a second. We believe that with our existing technology, we could easily do about 200, 250 flows a second. But again, our goal is millions of devices, billions of metrics, which can mean virtually unlimited flows. So that brings in Sentinel. So the idea of Sentinel is this. I've got all these little daemons. I've got a daemon that does service assurance, like a service check. It's polar D. I do a daemon that collects data via JMX, SNMP, et cetera, called collect D. And I manage traps, and I manage syslogs. And I want to be able to scale that. So the idea is to create a standalone system, which we call Sentinel. It's a runtime environment that allows us to run portions of these processes, which all used to live in one VM on OpenNMS, out to different sites. And the first one we're doing, because that's what we got paid to do, is Telemetry D. Now, so here's a kind of a busy slide. It actually shows up really good on this beamer. So, but I want to explain this slide. Remember I told you about the Minion. So Minion allows us to gather remote data. Well, I have a remote office. I can have a couple of Minions. So the Minions automatically deal with failover. So if one of them, so you usually want to put 2 Minions in a remote site in case one fails, the other one will keep working. So I have my remote office with a couple of Minions. I got another remote office with a couple of Minions, and I'm generating events, data collection, and flows. And that all gets sent to the internet. You can run the Minion on a phone. I think it's only Android right now. It might be iOS, but so you can run the Minion on the phone, and this all gets sent to a Kafka messaging bus. So the collection of data can scale. The more Minions you need, you can put Minions in your data center. So as many Minions as you need, you put out there. So that scales. Kafka can be clustered. So it scales. I love problems that can be solved with money. I don't know how many of you have ever done consulting, but you'll go to your customer and they'll say, like one of the things we used to use before Cassandra, and we still support it, is RD tool. RD tool was a great little storage protocol. And I'd go in and I'd say, well, how much data do you want to store? And they go, everything. And I'm like, well, we can't store everything. Oh, you suck. And now I go in and I say, what would you store? Everything. I'm like, okay, you'll need a Cassandra cluster. You'll need 50 nodes. They'll run $10,000 each. And then they go, oh, maybe I don't need everything. And that's great. So Minion scale, Kafka scales. The point of Sentinel, which is this here, is to offload from your main OpenNMS app all this functionality. And then that gets sent to either Postgres or Elasticsearch or Scylla/Cassandra, and all three of these can be clustered and can scale. Just to use a buzzword, you can even use Kubernetes to spin up and spin down your Sentinels. So let's say for some reason your applications are getting slammed. Maybe it's a big sale day. Maybe you're doing some sports things and it's World Cup or something like that. Well, you could scale up to 20 or 30 Sentinels, and then when they slow down, you could scale back down to 2 or 3. So Sentinel is key to getting this unlimited data storage. And that was introduced in Horizon 23, just for telemetry data, but we hope to add everything else later. Now the cool thing, and I think I've got enough time to do this, I could sit here for the next 7 hours and talk about OpenNMS, so I'm trying to keep it within the time. We've added another project called Sextant, which is machine learning. So if you have these millions of alarms, how do you act on them? How do you filter them? How do you deal with them? Well, we have to do something, and we've decided we're going to implement machine learning. So how does it work? So what we end up doing is we analyze various syslogs and traps and events that come into OpenNMS. And based upon them, we create a topology. And then using that topology, we can cluster alarms using a protocol called dbScan. Not a protocol, I guess it's an algorithm. Using an algorithm called dbScan to cluster them together in something we're called situations. So the idea is something goes wrong on your network, you get flooded with events. Instead of having to deal with 100 alarms, you deal with one situation. Now, so how does that work? So we collect these alarms, and then we create models. I'm just going to jump over here. So we know what nodes are. So let's say I get a syslog event that says there's a duplex mismatch between node A and node B. Well, I know there's a link between node A and node B, so I'll store that. And then I might get another message which indicates that there's a problem with a link at the interface level. And so I can model the SNMP interfaces that are associated with a node. Now, this is something that you can't do ad hoc as of yet. I mean, it's in the code. We take specific events and we create this. But we've done it for VPN tunnel events, BGP peer events, the entity MIB, so you can get issues between cards and boards and things like that. And don't freak out when you see this. Okay, so this is part of our topology map. But you won't see this in OpenNMS. The people I work with, my one talent, my superpower, is getting amazing people to work with me on things. That's all I do. I run my mouth and I get really smart people to work with me. Well, the really smart people have created an integration with OpenNMS for GraphML. So you can define a graph using GraphML and load it into OpenNMS. Well, to diagnose issues with Sextant, they allow you to export it as GraphML, and then you can load it into OpenNMS. And so this is just a small section of a particular part of this map, but this is a particular node. So you have a node here, and then these are interfaces. And you can see these are alarms. These two alarms are associated directly with this node. And then these alarms up here are all associated with this interface, this gigabit interface, and they are all coalesced into that thing called a situation. We're working on better icons for this. This is kind of Horizon 24 stuff. And then over here, similar thing. We've gotten these 3 alarms that happen to deal with this interface, and we've clustered those together into a situation. So there's no magic. One of the things I hate about IT is so many people, it's magic. Have you ever, hey, I'm having a problem. Did you reboot? Why do I need to reboot? I'm like, well, you need to reboot, because that's magic. You know, if you put on a white robe and come in at midnight during a full moon and you sacrifice a chicken over the server, it'll fix the problem. And I'm like, I don't want any magic. I want to show you how we do this. So We use this thing called dbScan, which stands for Density-Based Spatial Clustering Applications with Noise. And it's basically, it's math. It's one of the most popular machine learning algorithms, according to Wikipedia, which is where I got this picture. So the idea is, okay, I have this distribution of data, and I want to group it together somehow. So I'm like, does this spot belong with this spot? Does this spot belong with this spot? Well, these spots seem to belong together, so maybe I'll do it on distance. So I'll choose a number called epsilon. And if anything is within the distance of epsilon, I'll cluster it together. So I might end up with this. Let's say I randomly chose epsilon equals 100. And so these are all within 100, even though this guy's kind of far out. He's just close enough to these guys to count in this cluster. But this guy here and this guy here and this guy here, they're noise. And so I've created two clusters. One of the reasons we chose dbScan is it's one of the few machine learning algorithms that doesn't require you to know the number of clusters in advance. So you can set it may find 2 clusters, it may find 100. Whereas a lot of the other ones you say, I have this data set and I want to put it in 10 clusters. Okay, then it can do it. But if you don't know the number. So, are you ready? I heard you're all technical. Okay, we got math. Ready to do some math? So the way you read this function is we determine the distance between alarm A and alarm B based upon 2 terms. The time between the alarms, the time of A1 minus the time of A2, and the number of hops, the distance between whatever caused A1 and whatever caused A2. Now, this beta is a weighting function. How much do we want to care about time versus distance? So as you can see, for the time, these little bars mean absolute values. So we take the absolute value of the time between the events, divide by 1,000. This is in milliseconds. So we divide by 1,000, which is of seconds. And then we divide by 60 to get minutes. I'm not sure why we have to get to minutes, but that's what we do. And then we multiply this times beta. And then on the distance side, we take the distance between A1 and A2 times 1 minus beta. So it'll average, it'll sum to 1. And then we multiply the whole thing by this coefficient called alpha. And alpha happens to be 781.78. Kind of random number, doesn't it sound? So we were actually hired to replace a product called Cisco Prime Network. And what Cisco Prime Network does is alarm correlation. So we had this huge corpus of syslog and trap data. And so we shoved it into OpenNMS, the OpenNMS correlation engine, which is the OCE. We shoved it into the OCE, and we kept fiddling with alpha and beta until we got the closest match to what Cisco Prime Networks did. So in your network, this may change. You can fiddle with these values. Alpha and epsilon are kind of related if you think about it. So alpha is just an overall coefficient for distance. Epsilon is the distance itself. So you want to keep one steady and fiddle with the other one. You wouldn't want to play with both unless you're just super smart, because I don't know how that'd work. So let's bring this home with an example. So let's say I got a node loss service event, HTTP, and 2 seconds later I got a node loss service event, HTTPS. In OpenNMS, this would be from service checks. So I'm going out, I check port 80, it fails. I check port 443, it fails. So I generate 2 alarms. And they're 2 seconds apart, 2,000 milliseconds, 2 seconds apart, on the same device. So let's plug that into our distance equation. So this piece, since the distance between A1 and A2 is 0, it's on the same node, this whole term goes away. And so if I take my 2,000 divided by 1,000 divided by 60, multiply it by beta, which if you remember is 0.53, I end up getting this number, fairly small number, 0.0177 times 178.78 is 13.81, which is less than our epsilon of 100. So these 2 alarms would be correlated. Now, what if they happened on 2 nodes 1 hop away? If that happens, then this term is no longer 0. So node A gets a node loss service, and 2 seconds later I get node B. Well, what ends up happening here is that this term actually plays a big role. So when we get down here to this 78178, you'll see that it's not correlated. Now, if it happened in a very, very short amount of time, maybe it would be correlated. I mean, you could figure that's kind of what it's saying. And most of what we're dealing with in this scenario are syslogs and traps, which are received asynchronously by OpenNMS. They just boom, boom, boom. So it's not like a poll. So they do happen all at one time. Does everyone get that? Does everyone see how this? We're basically just choosing a distance, and if everything is within a certain distance, we cluster them together. Now this is in production, so I've got a slide of what it looks like in OpenNMS. And so basically we got a link down trap from SNMP, and we got two syslogs, all on the same node. And so we got a line protocol down, we got a link down syslog, and then we got an agent down trap, link down trap. And what happened was those all got correlated together. And there's a little piece here called the Oce Diagnostics. It says the alarms happen within 1.78 seconds across one vertice or one node. And so that's how we do correlation. And the customer is actually using this now, and they're no longer paying Cisco for Cisco Prime Network. So where do we go from here? Well, we've got, this is all unsupervised. Like, you just start shoving. At this one customer, we're doing around 10,000 syslogs a second times a number of different devices. And it's on a Minion. Now, Minion's not running on a Raspberry Pi. It's actually running on a fairly large server. But you can collect and process this kind of data. What we want to do is add some semi-supervised learning. So we want to allow the operator to say, hey, these two things are not related. And so we have a little GUI that pops up so you can hit these little X's and say these things aren't related. Or you can say, eventually we'll have it so you can pick two alarms and say these are related and we need to deal with them. And so I've modified our original equation to add this repulsion factor, which will increase the distance. So if these two things aren't related, then we'll add some amount of distance to say, hey, these aren't related. And then if they say they are, we'll have an attraction factor that will say, hey, these things should be related, so decrease the distance. And then we use gamma. I just threw that in there as a weight. So we might want to weight the repulsion factor much greater than the attraction factor, because we don't want this to, if these two things aren't related, we definitely don't want them correlated. And that may be more important than actually correlating things. Now, of course, the step after this is to make situations out of situations. So can we correlate situations into meta situations? But that's neither here nor there. But we believe by adding these tools, network monitoring people can actually start to love their job again. And they can get a lot of information, and maybe we can get to the monitoring love. Now, we have just a few minutes for questions. If you look at my, my little abstract, I mentioned MQTT. OpenNMS does support MQTT, and this is taken from the GitHub page of the MQTT plugin. We're here on Thursday for the hackathon. And so if you have any interest in MQTT, there's actually a presentation right after this on MQTT, which I plan to go to. We're going to be, Ronnie Trommer, who works with us, he and I are going to sit down on Thursday and start playing this using OpenHab. Any questions? Was this useful? Enjoy it? So, yes, sir?
We should give it another time, I think, because it was much more interesting than it looked like. I was really busy, and Bernd is like, dude, are you coming? And I was like, yeah. And so I didn't know what to talk about. So tell everybody. So wander around and tell everybody, you missed it. It was so good. So you can watch it online. So if you're watching this online afterwards, see what you missed. I'll be here next year. So,
great.
Anything else? Thank you very much.
Yeah, I have a question.
Sure.
Like the attraction factor and the repulsion factor, which you talked about. Like this is stored then for later usage also.
Yeah,
like if the same event occurred, and
our development office is actually in Canada, and I went there to create the slide basically, and I was talking with the team there. This is something, this exists, but we haven't figured out quite what we're doing with it yet. So the first time that equation's been written down was like a week ago. But yeah, the idea is that we would store this somehow. And we get rid of the timestamps, but basically for these particular nodes, and add this idea that, hey, this is these things aren't related. Maybe they happen at the same time, but for whatever reason, they're not sympathetic, and so we need to get rid of one of them. But the idea is to allow, anytime I let a computer do it on its own, it tends to work fine for about 80% of the time, and the other 20% is just horrible. It negates the other 80%. So we wanted to add a method where operators could go in and say, oh, okay, don't bother me with this anymore. Let's separate it. And that's kind of the plan moving forward.
That's the self-learning plan afterwards.
And this is the supervised where someone could actually can and apparently the specific term is semi-supervised, because I'm trying to make sure I got all my terms right. So semi-supervised machine learning. But yeah, so the idea is, this would be stored somewhere, and then as the things will process, we would increase or decrease the distance of the alarms based upon this knowledge. Make sense?
Cool. Yeah. Next question.
Sir.
Hi. Thanks for the nice talk.
Oh, thank you.
I was using with OpenNMS some time ago in a quite sophisticated environment. At that time, we installed all manual. Now, in my current role, I'm looking for automation across the board.
Okay.
Now, let's say I would like to use OpenNMS in projects. What kind of methodologies are supported by deploying and rolling it out with all your options fully automatic?
So we do an incredible job of packaging. So we have a Yum repository, so you can type Yum install OpenNMS. We've got a Debian repository, and we make RPMs for every branch. So if you wanted to follow this work, you could go to our Jira, find out what the Jira issue was, look that up to figure out what branch it was, and then you could just update it every day that there was a change. But we also, there's chef recipes, we use Ansible, so we use Ansible to deploy OpenNMS. Is that getting the thumbs up for Ansible? And I believe there's also Puppet. It's not recipes, but...
How do you do the configuration with Ansible? You change configuration files?
Oh.
Or you use the API to connect?
Yeah, that's a good question. There isn't actually... You can use Ansible to change the configuration files. What we're hoping with the minions and things like that, so to back up, we have a lot of customers who used to deploy maybe 20 OpenNMSs. So how do you deal with that? Now, all of the configuration of OpenNMS is pretty much in a single directory. So a lot of what they would do is they would set up some kind of rsync and restart to migrate. So they add a new person to the team, that gets updated in our users file, and they have a notification path, and they might add a new MIB or a new alert. That would just get all pushed out. Now with the Minion not only sends in collected data and alerts and traps and syslogs, the Minion includes a location. And so what you could do is, you could just have the one OpenNMS. So you install it, you configure it in one location, and then deploy minions in every other remote environment. So it could be a customer environment, et cetera, and have all that come to OpenNMS, and then the configuration would only exist in one place, and you wouldn't really have the need to spin it up on multiple instances. I have a Minion at my house, which I love, because the other day it stopped working. It had been working for like 2 months. It stopped working. So I'm like, I run on a little Intel NUC. So I've got CentOS 7 on it. And I said, what's going on? So I figured maybe it was something wrong with the operating system or something like that. So after trying restarting and everything, I copied there's one little configuration directory. I copied it out of the way. I completely based the box. I erased it. Reinstalled Minion, copied that directory back over. Still didn't work. Turned out I had a duplicate IP address. So I had this temperature sensor in my workshop, and I guess it just didn't work for 2 months. But it came on, and it was interfering with the Minion. So once I changed the address, but what I learned was, unlike OpenNMS, where you'd have to back up the configuration and back up the database and back up your RRDs, I just blew it away and put it right back. And that's the idea, is that these are kind of throwaway things. It uses this thing called a competitive consumer queue. So your minions go to OpenNMS and say, what work do I need to do? What work do I need to do? And then it will actually send the information back and say, okay, Minion A, you do this work. Minion B, you do this work. And if Minion B goes away, Minion A will do all the work. Which was funny. We had a customer who had 2 minions, And he said, it's saying my Exchange server is down 50% of the time, but it isn't. It turned out he had a bad firewall rule. So Minion 2 could not get to the server, but the first Minion could. And so half the time it said, oh yeah, it's up. And then half the time it said, oh, it's down. And once he fixed the rule, so he had 50% availability on that one server. So that's kind of what we're saying right now instead of having to distribute it. And again, all of the Sentinel and all the Minions get their configuration and information from the central OpenNMS, so you don't really have to do what you did in the past. Anything else? Thank you very much. Please enjoy OSMC. Come drink beer with me tonight.